In this video, I would solve a comprehensive example for lateral earth pressure, which includes a sloped ground and a wall that is not vertical. So the parameters given for the problem are shown here. The height of the wall is 12 feet. Gamma of the soil behind the wall is 105 PCF or pounds per cubic foot. The soil is granular. Phi prime is 30 degrees and C prime is 0. The angle of theta is 5 degrees and the slope of ground is 10 degrees and the friction angle between the wall and soil on this interface is 2/3 of phi prime or 20 degrees. We also have earthquake effect with KH of 0.2 and KV of 0. And we need to find the active earth pressure distribution and resultant active force, passive earth pressure distribution and resultant passive force, and active earthquake pressure distribution and also its resultant force. We also want to use Coulomb's and Rankine's formula. So we start with the active pressure and Rankine's theory. So since this is a generalized problem in which the slope is ground and the back of the wall is not vertical, you should use this formula we have already talked about to find psi A, and you just need to be careful if you're using this formula. Arc sine of sine 10 divided by sine 30 would be in radians, so be careful about this. So this would be psi A would be 0.3547 radians, and if you use Ka for Rankine's active force, you're gonna find this value to be equal to 0.3859. So this is the lateral coefficient Ka, and Pa would be half of Ka times gamma h squared, and if you find this, it would be 2917 pound per foot, which means per length of the wall perpendicular to the surface, because this is a plane strain problem. And this would be definitely be applied at 1/3 of the height of the wall from the bottom. You can also find Ka using Coulomb's formula, and Ka for this one would be very close to Rankine's Ka, which is here it is 0.3857, very slightly smaller than Ka of Rankine because of the effect of the friction between the wall and the soil, and the resultant force basically would be the same, and again it's gonna act at 4 feet from the bottom of the wall. There is an spreadsheet I have prepared for you, and you can subscribe and freely download it. You just need to give the input values we had, like the ones we have here. So phi prime is 30 degrees, theta was 5 degrees, delta is 2/3 of phi prime, which is 20, and alpha is 10 degrees. The soil is normally consolidated because we do not have any information about over consolidation, so we assume that it is normally consolidated. And KH is 0.2 and KV is 0. So if you see, you will have all of these values here. The at rest would be 0.5. Active Rankine would be 0.3859 as we found in the slide, and active Coulomb would be 0.3857 as we found together. Now let's move on to the passive forces. So for Rankine's theory, you should find psi p again in radians, and if you find kp, it would be definitely a larger value compared to ka and k0, and it would be 2.8778. And pp, actually this one should be pp, this is also pp, which is the passive force, would be half of kp times gamma h squared, which would be 21,756 pound per foot. And again, this will be applied at 1/3 of the height of the wall from the bottom of the wall. So pp would be this value. One important thing that you should pay attention to is that kp for Coulomb's theory would be a very large value as compared to Rankine's theory. And what is the reason for that? The reason for this difference is considering the friction between soil and wall. This one helps a lot when you want to push the wall against the soil. This friction on this interface would give you a very large value when you consider it, and that is the reason that we have a very large kp using Coulomb's passive equation compared to actives, compared to Rankine's pressure. So if you again check the Excel file here, you can see that the passive coefficient from Rankine theory and passive pressure from passive coefficient from Coulomb's theory are correctly found in this spreadsheet, and you can easily use that for your problems. The next thing, which is more important, is finding the active earthquake pressure. So if you remember, we needed to find beta bar, which relates to kh and kv. Here kv is 0 and kh is 0.2. This would be 0.1974 radians or 11.3 degrees. KAE using Mononobe-Okabe equation will be this value, and we have found it in our spreadsheet here. It would be 0.6324, and PAE, which is static plus dynamic increment load, will be found using this formula. So this is the total force, which includes static component and incremental dynamic force. So the incremental dynamic force delta PAE will be found as PAE minus PA. This comes from Coulomb's active force. We already found it in this slide. So delta PAE would be 1864 pound per foot. And if you remember, we have these steps for finding the location of the force. Step 1 was finding the Coulomb force, PA, which was 2917, applied at 4 feet from the bottom. So this is 2917, and the active dynamic force, the total value is 4781. The increment, as we found together, is 1864, and it will be applied at 0.6 times h, where h is the height of the wall. It would be 0.6 times 12, which would be 7.2. So this will be applied at 7.2, and its magnitude would be 1864. The point of action of the total active dynamic force PAE now will be found as L bar. So you just basically needs to take the moments of these forces from the bottom, and if you found this value, it would be 5 25. This is a very comprehensive example that includes all of the concepts we already talked about before.